Okay, so let us begin today's lecture. Today we will embark on probability theory. So what is as a brief outline, we will discuss from counting to probability, various examples where probability is in action, independent events, conditional probability, and so on. So as a motivating problem, let us take the famous birthday problem. So what is the birthday problem? So let us take the example of this lecture theatre, and all of you have your own birthdays, and suppose someone offers you the following bet that there are two persons in this lecture theatre now with the same birthday. Okay, so of course you might not believe it, because there are 365 days in a year, and although there are close to 365 students enrolled for this module, not so many are present, right? So you might imagine that the chance that there are two people having the same birthday present in this room at this moment that chance is pretty low. But we will see that it's actually not that low. So that's one of the an example of counterintuitive things which you understand when you analyze this sort of situations carefully from a mathematical point of view. So this analysis of this kind of situation will involve the study of the mathematics of chance, and the other name for the mathematics of chance is probability. So that's why we are here today discussing probability. So the goal of probability theory is to model uncertain situations and quantify the uncertainties involved. Okay. So here is another motivating example. So this is the famous Monty Hall game, and some of you might have encountered it as a popular quiz in a party. So what is it? So suppose you are in a game show, and suppose that there are 3 doors, and you are asked to guess the door behind which there is a grand prize, say a Ferrari. Okay, so you want to win the Ferrari, of course. All of us want a Ferrari if possible. And after you pick, you have 3 doors, and there are ghosts behind 2 doors, and your grand prize, which is a Ferrari, behind one of the doors. And your goal or your target is to find the Ferrari, find the door, select the door which has the Ferrari. Of course, you can never do it for sure, but under any given circumstance, you want to maximize your chance of picking the door which contains the Ferrari. Okay. So the Monty Hall problem on the Monty Hall game is as follows. So the main the trick or the interesting part about the game is that it gives you a second chance. So in the Monty Hall game, you first choose a door, and then, of course, only one door contains Ferrari. So you have 2 doors, which you have not chosen. So we have picked one door, and there are 2 other doors which might or might not contain Ferrari, but at least one of them for sure contains a goat, right? So the game show host, what he will do is that he will open the door which contains a goat, or if there are 2 doors which contain a goat, both of which contain a goat, he will pick one of the doors which contains a goat and show you the goat. And now the situation is as follows. You have picked one door. There are 2 doors remaining, out of which one is open, and you can see a goat inside it. So now your dilemma is to whether you choose the other door. So you have still one door closed, and your dilemma is to whether you switch your allegiance from your current door to the other closed door, or whether you stick to your current door. Okay? So, in other words, do you improve your chances of getting do you improve your chances, or do you maximize your chances of getting a Ferrari by switching to the other closed door from your current choice? So, the question is, should you switch your choice? So, all these are related to, all these can be understood in terms of probability theory. So, that's why we are all here to study probability theory today. So, let's now take, but these you may, as you may understand, the birthday problem or the Monty Hall game, these are somewhat sophisticated problems involving probability. So, to understand the mathematics behind these problems, we have to take a step back and we have to sort of cover our bases and understand the basics of the mathematics of chance, and then only we will be able to approach these problems. So, so how do you build a mathematical understanding of chance? So, recall that in the game of poker, you have a standard deck of 52 cards, which contains 4 suits, and each suit contains 13 cards, etc., as we have seen before. So, out of these 52 cards, in poker, you always talk about hands. So, a hand in poker is 5 cards out of these 52. And we have seen that you can choose 5 cards out of 52 cards. In 52, choose 5 possible ways, which you can enumerate as 2, 5, 9, 8, 9, 6, 0. So, if you look at all the possibilities of having a hand of 5 cards, there are 52 choose 5 possibilities. So, if you think of intuitively, if you think of picking a hand of poker cards randomly, okay, make a random choice of a poker hand, it will be a random choice out of these 52 choose 5 possibilities, right? So, the total universe of possibilities, the total set of possibilities, which is a set of all possible 5 card hands, where your random poker hand can belong, is called the sample space. So, a sample space is the total collection of all the possibilities out of which you will be making a random choice. Okay? So, now, if you ask intuitively, if you ask for the chance that, okay, suppose I just randomly pick a poker hand, what is the chance that it is a royal flush? Now, we have seen in the previous week that a royal flush, so a royal flush means that you have 10, jack, king, queen and ace. So, these 5 cards. So, in how many ways can you have a royal flush? Well, the only variable in a royal flush is that the numbers of the cards are fixed, and the only parameter you can control is the choice of the suit. So, there are 4 suits, each suit contains a royal flush, and so there are 4 ways to choose a royal flush, because you can pick any particular suit, and from this particular suit let diamonds, and then once you have chosen your suit to be diamond, there is only one way to pick a royal flush, which is to take the 10 of diamond, jack of diamond, queen of diamond, king of diamond and ace of diamond. Okay? So, there are only 4 ways of choosing a royal flush, and out of a total possibility of 2, 5, 9, 8, 9, 6, 0 ways of choosing a poker hand. So, if you just intuitively, if you just pick a poker hand at random, then the chance of having a royal flush should be 4 over the entire universe of possibilities, right? If all the flushes, or if all the hands had somehow their, there's an equal chance of getting any hand. So, out of these 2, 5, 9, 8, 6, 2, 5, 9, 8, 9, 6, 0 possibilities, only 4 are royal flushes. So, the chance of getting a royal flush in a random draw of a poker hand should be 4 over 2, 5, 9, 8, 9, 6, 0. and you can calculate this as 0.000154%. So next you can ask for the chance of getting a 4 of a kind, again intuitively in this sense. So the chance will be the number of ways of getting 4 of a kind, which we had discussed before, and divided by the total number of possible poker hands. So this will turn out to be 0.0240%, which is again it's considerably larger than the chance of getting a royal flush, because of course 4 of a kind is more common. There are many more ways of getting a 4 of a kind, whereas there are only 4 ways of getting a royal flush. So this explains why the various poker hands are ranked in that way. So the royal flush is of course considered to be very important in poker because it's very rare to get a royal flush. The chance is so low. Whereas 4 of a kind, it's much more likely to get a 4 of a kind. It's the chance of getting a 4 of a kind in a random poker hand is much higher, so it's kind of less. It's more 4 of a kind is much more common than a royal flush, so its rank is lower. Okay, its rank is below royal flush. So in order to study, so this motivates a more formal study of the mathematics of chance. So in order to study probability or the mathematics of chance, the first thing which we need to understand is the concept of experiments or random experiments. So what is an experiment or a random experiment? So experiment is a situation whose result or outcome depends on chance. So here by experiment we mean random experiment. Okay. So it's a situation whose result or outcome depends on chance. So for example, tossing a coin. So there are 2 possible outcomes, head or tail, and when you take your coin and you are about to toss it, you never know whether it's going to turn up head or tail. You only know depending on the bias of the coin, maybe it's more likely to get a head or more likely to get a tail, or maybe if it's a fair coin, maybe it's equally likely to get a head or a tail, but you can never know for sure what's going to happen, what outcome you are going to get, right? So it's tossing a coin is an example of a random experiment because the outcome possible, the actual outcome out of the 2 possibilities, head or tail, depends on chance. You have no control over it. Another example is throwing a dice. There are 6 possible outcomes, and any of these possible outcomes can materialize with varying probabilities. In particular, if you throw a fair dice, which is analogous to a fair coin, so all the 6 possibilities 1, 2, 3, 4, 5, and 6 have equal chance of turning up. So you can get 1 with probability 1/6 if your die is fair, right? So, but even if the die is loaded in favor of one face, you can still, it might so happen that you might still get a face which is less likely, right? The only thing is that the chance of such an event happening is small, but you can still get suppose the die is loaded in favor of 1, so like maybe 90% of the time you are getting 1, and the rest of the faces in total occur with just 10% chance. But even then, before you roll the die, you do not know what is going to turn up. With a ever so small chance, maybe 2 or 3 could appear, right? So that's why throwing a dice is a random experiment. Another random experiment is picking a card from a deck, and that's why card games are so popular, because there is this element of chance. So there are 52 possible outcomes of picking a single card. There are 52 possible cards, so you can choose any of them, and if you choose randomly, you don't know what's going to happen. That's another example of a random experiment. Tossing a coin twice is another experiment, another random experiment, and this time what are the possibilities? So your 2 coins, both could turn up heads. One could be head, the other could be tail. The first one could be tail, the other one could be head, and then both could be tail, and so on. So so this is, so the set or the universe of all possible outcomes of a random experiment is the sample space. Okay. Any questions? So, the set of all possible outcomes of an experiment is called a sample space associated with the experiment. So, an element of the sample space is called an outcome of the experiment. So, for example, if you toss a coin, the sample space, the collection of all possible outcomes is head and tail. So, that is the sample space. And the individual elements of this set of possible outcomes, like a head or a tail, is an outcome of the random experiment. For throwing a dice, the outcomes could be any of 1, 2, 3, 4, 5, and 6. The collection of all the outcomes is a sample space. Picking a card from a deck. So, so here there are two symbols. So, the first symbol denotes the suit, and the second symbol denotes the number. So, this is the first one is the ace of spades, or you could pick the 2 of spades, and so on until So, queen of clubs, king of clubs, and so on. So, this is so picking a card from a deck also has a finite number of possibilities. So, each one of these possibilities, like ace of spades or 2 of spades, is an outcome, and the total collection of all the outcomes is the sample space. And then tossing a coin twice, as we saw in the last slide already, the totality of all possibilities, which is a sample space, is HH, HT, TH, TT, right? So, so there are these some basic random experiments which are sort of very useful for understanding the various ideas in probability theory, and also if you, from a more practical point of view, setting exams in the question also often go back to these simple random experiments like tossing a coin or rolling a die or some combination of these, etc. So, these things, these random experiments, although they might be simple, they are quite important actually, and you can understand most, if not all, of the main concepts, important concepts in probability by looking hard enough into these simple random experiments. Okay? Any questions? Okay. So, let us now go to the concept of an event. So, an event associated with a random experiment is a subset of the sample space. So, for example, in the experiment of throwing a coin twice, you can think of the event that you are getting the same result twice. So, the result of both the coin tosses is the same. So, either both are heads or both are tails. So, of course, there are two outcomes which lead to this event. So, you can think of the event as a subset of this set. Okay? So, the event A corresponds to a collection of outcomes that is a sub-collection of the total possibility of all the outcomes. Okay? So, that is an event. In the experiment of throwing a dice twice, you can throw 2 dice together, roll 2 dice together. So, you could get 1 1 or 1 2 and up to 6 5 6 6. So, anything between 1 and 6 can happen can turn up for the first die, and anything between 1 and 6 can turn up for the second die. So, in total there are 6 times 6, which is 36 possibilities. Okay? There also you can ask for the event that you get the same number for both the dice. So, there are 6 possibilities which lead to this event, that you get the same result for both the dice when you roll 2 dice together. So, both the dice could turn up to be 1, both of them could turn up to be 2, both of them could show 3, they could show 4, 5 or 6. These are all the possibilities, because they have to show the same number, and this number has to be between 1 and 6. So, that is pretty much all that you have. So, out of the totality of 36 possible outcomes of this random experiment, there is a subset of 6 outcomes which lead to the event that both the dice show the same number. Any questions? So, here is a very important concept. This is it's called the concept of being equally likely. So, if all the outcomes, and this models many simple random experiments. So, if each outcome of a random experiment has as much chance of occurring as any other, then we call them equally likely. So, this is a kind of fairness. There is no preference for any particular outcome over the others. So, the most famous or the simplest basic example of this is tossing of a fair coin. So, you take a coin and you toss it, and if the coin is what we think of as fair, it means that head or tail has equal chance of occurring. So, head versus tail is 50-50. So, that is what we think of as a fair coin. And the concept of being equally likely in probability theory is exactly the math way of formalizing this. So, it is exactly saying that you think of your tossing of a coin as a random experiment. So, in terms of the math formulation, you think of the sample space. So, the sample space consists of head and tail. So, there are 2 possible outcomes, and you say that it is a fair coin when both the outcomes H or T have equal chance of happening. Okay? So, tossing a fair coin, the probability of H, we will come to it in a moment, is taken to be 1 in 2. Tossing a fair die, each of its 6 faces are equally likely. Okay? So, if you toss a fair coin, we often say that the coin being fair is the same as saying that head and tail are equally likely, which is saying that the chance of getting a head or a tail is 50-50, and if you express 50 out of 50%, if you express 50% out of a total 100% in terms of a fraction, you get 50 over 100, which is 1/2. So, the chance, if you express it as a fraction, then the chance of getting a head and the chance of getting a tail are the same, and this chance is 1/2. Okay? So, that is somehow the intuitive way of formalizing it. But notice that if you look at the event that you get a head, then there is only one outcome which leads you to the event that you get a head, and you have 1 on the numerator. So, think of the probability of head being equal to 1/2. So, let us sort of dissect this statement. Notice that out of the total sample space, total number of possibilities, total possibilities of the random experiment, there is only one outcome which favors a head, getting a head, and you have 1 in the numerator. And in totality, there are 2 possible outcomes in the sample space. So, and you have 2 in the denominator. So, this is a Q. So, now we will take a jump, a leap of faith, and say that let A be an event in the sample space. So, the sample space is the totality of all possible outcomes, and A is an event. So, A is basically a sub-collection of the possible outcomes. So, A is a subset of the sample space. So, and we are working on under the situation when the various possible outcomes of the random experiments are equally likely. So, there is a fairness involved in the random experiment. Then the probability of the event A is, because A is a subset, it means that it has a certain number of outcomes inside A. So, you can take the size of A, cardinality, the size of A as a subset. So, the total number of possibilities which lead to the event A, and divide it by the total number of possible outcomes of the random experiment, which is the size of the total sample space. And if you take the number of possibilities which lead to A divided by the total number of possibilities, you call that number the probability of the event. So, this is the definition. Of course, we are working under the equally likely scenario. Okay, any questions? So, in a way, it's so there is a something quite slightly subtle here. So, it's not that there is some God-given notion of probability and we are establishing that the probability is actually equal to the size of the probability of A is equal to the size of A divided by the size of the sample. So, it's not really that. What is happening is that we are observing that in many natural situations, particularly when fairness or equally likely idea is involved, the ratio of the size of A divided by the size of the total sample space is a good measure of the chance, of the natural intuitive notion of the chance that the event A might occur. And then we are taking a cue from, so we have seen that in some examples. So, we have seen that in the example of tossing a coin, for instance, and then we are taking a cue from there and we are defining the notion of probability of an event, like concretely as a definition in science, to be given by the relation that the probability of an event A is the size of the A when you imagine it as a subset of the set of all possible outcomes divided by the size of the total sample space or the total number of possible outcomes of the experiment. Okay? Questions? So, thus we see that computing the probability of an event basically involves counting. Okay? Because if I ask you to calculate the probability of an event A, then by this equation, what you will do is that you will go to the random experiment, think about it hard, calculate the total number of possibilities, possible outcomes of the experiment, so that your mod S, and then calculate the total number of outcomes possible for the experiment which lead to the event A, which is mod A, take their ratio, and that will be your probability. So, really counting the number of outcomes which belong to A is going to be important for calculation of probability. So, look at the random experiment. For example, look at the random experiment of tossing a coin 3 times. So, now the sample space is all possible strings of length 3 which contain H or T for each entry. So, it could be HHH or HHT or any combinations of H or T of length 3. And your event again is our favorite event, which is getting the same result in all the tosses. So, what are the outcomes which favor the same result? What are the outcomes which lead to the event that there is the same result for all the tosses? So, this same result could be either head or tail. So, either you get head for all the tosses or you get tail for all the tosses. So, the outcomes of the random experiment which favor the event A, which lead to the event A, are HHH and TGT. So, the probability of having the same outcome for all the tosses is the size of A, size of the set A, which is 2, divided by the total size of the sample space, or the total number of possibilities for the entire experiment. So, how many possibilities are there for the entire experiment? That is equal to the total number of strings of length 3 which you can make out of the 2 digits H or T, right. So, let us now count how many strings of length 3 you can make out of 2 characters H and T. Well, you think of the length of string of length 3 as to be made of 3 placeholders. So, in the first place you can put either H or T, so you can fill it up in 2 ways. For each way of filling up the first spot, you can fill the second spot also in 2 ways, H or T, and so that's times 2. And for each way of filling up the first 2 spots, you can fill up the third spot again in two ways by h or t, so that's another times 2. So total 2 cubed, which is 8. So you divide by the total size of the sample space, which is 8. So this is 2 over 8, which is 1/4. So if you toss a fair coin 3 times, then the chance of getting, the probability of getting the same result for all your tosses is 1/4, 1 out of 4. Okay? Any questions? So if there are no questions, let's take a 10-minute break at this point, and we will continue after the break. Okay, so let us continue with the lecture. So in the before the break, we considered the scenario of equally likely or a fair situation, and in that sort of situation, we saw that we could define the probability of we could give a natural definition for the probability of an event to be the number of outcomes which lead to that event divided by the total number of possible outcomes of the experiment. Okay. So now let us take another example of this. So let's calculate the probability. So if you toss a coin 6 times in a row, what is the probability that you get more heads than tails? So let's analyze this. So first of all, let us calculate the total number of possible outcomes of this random experiment. So what is the experiment? So the experiment is that you take a coin, a fair coin, and you toss it 6 times in a row. So the possible outcomes are each leads to a possible outcome of a head or a tail. So the possible outcomes are sequences of heads and tails, right? And sequences of length 6, because you toss the coin 6 times. So you can represent each outcome as a sequence or as a string of length 6, and each entry is head or tail. And in total there are 6 entries. Okay? So each entry is head or tail, right? So how many possibilities are there? Well, you do the usual yoga. You calculate it like you did in counting. You can fill the first position in the string by a head or a tail in 2 possible ways. For each possible way of filling the first position, you can fill the second position in another 2 possible ways. So that gives you 2 times 2. Then you go to the third position, which gives you another times 2. So you get 2 times 2 times 2 for the first 3 positions, and if you go on, then you see that you can fill the 6 positions, each position with a head or a tail, in 2 times 2 times 2, 6 times. So 2 times 2 times 2, 6 times, this many ways. So this you can summarize as 2 to the power of 6. So the total number of possible outcomes of this experiment is 2 to the power of 6, which is 64. And that's the size of the sample space, because the sample space, as we noted, is the set of all possible outcomes of the experiment. Now, our event of interest, so if you look at the definition of probability, its probability is the probability of A is the size of the set A divided by the size of the set S. So you already have one ingredient in place, which is the fact that you have already calculated the size of the set S. So now you have to calculate the size of the set A in order to complete the calculation of the probability of A. So how do you compute the size of the set A? So the set A is a set is the event of having more H than T. So it is a collection of all strings of length 6 having H or T in each spot, so that there are more H's than T's. So of course there will be some strings with 1 H and 5 T's. Of course they are not good for A. 2 H with 5 T's, not good for A. 3 H and 3 T's. That's still not good for A, because you want more H than T. So it's not even good enough that there are equal number of H and T. So you need more H than T. So 4H and 2 T's is good. 5H and 1 T is of course good. And of course if you have all H's, then fine, we'll take. So these are the various possibilities, and let's count the number of possibilities in each case. So how many outcomes are there with 4 H's? So how many strings of length 6 are there with 4 H's and 2 T's? Well, you have 6 spots to fill, out of which you want to pick 4 spots for your H's. Once you pick 4 spots for your H's, you slot the H's in there, and the remaining 2 slots you just put T. So the total number of outcomes having 4 H's is exactly equal to the total number of ways of choosing 4 spots out of 6 total spots. Okay, clear? Excuse me. So this, as we all know, is 6 choose 4. What is the total number of outcomes with 5 H's? Well, that should be the number of ways of choosing 5 spots out of 6, because exactly in these 5 spots you will put your H's, and the remaining spot you will just fill with a T. So how many ways of doing that are there? Well, 5 spots out of 6 is 6 choose 5, which is 6. And how many outcomes are there with 6 H's? Well, all of them are H's, so you have nothing to count really. There's only one possible string with all 6 H's, right? So that's 1. So you sum all of them. So this is the total number of outcomes which lead to the event A. So that's the cardinality. That's the set. That's the size of the set A, if you think of it in terms of a set, and you divide it by the total number of possible outcomes of the experiment to get the probability of A as 22 over 64 or 11 over 32. Okay? Any questions? So, let's think of some basic probabilistic ideas which are often useful. So, one of them is the concept of mutually exclusive events. So, mutually exclusive event, if you can go back to the previous example and see. So, if you sort of focus on the event that you have more heads than T's, so of course that's an event, but you can fine tune further and focus on the event that there are exactly 4 H's, or there are exactly 5 H's. Of course there are events which are contained in the bigger event that there are more H's than T's, but you can also look at these individual events that there are exactly 4 H's or there are exactly 5 H's. Now if you think carefully, these 2 events that there are 4 H's or the event that there are 5 H's, they cannot happen together, right? Because if you toss a coin 6 times, you cannot, at the same time, you cannot have 4 H's as well as 5 H's, right? Because the number of H's is just going to be one number, right? So, these 2 events are called mutually exclusive because they cannot occur together. And in terms of sets, the corresponding set of outcomes do not overlap. They are disjoint. Okay? So that's the concept of mutually exclusive events. So let me just clarify a bit further by saying what is an example of an event, or what is an example of 2 events that are not mutually exclusive. Okay? So think of the event that, again, we are doing this experiment of tossing tossing a coin 6 times in a row. Okay? And we have already looked at the event that there are more H's than T's. Okay? So that's a legitimate event. Let's think of another event called that B, which is the event that that number of H is even. So you get a head an even number of times. So you get a head 2 times or 4 times or 6 times out of 6, right? Now notice that if you think of the event A, that there are more H than T, and B, that the number of H is even, both of these 2 events can occur together. Because, for example, if you get exactly 4 H's, you already have an outcome for which event A occurs because there are more H's than T's, and event B also occurs because the number of H is even, right? Because there are 4 H's, and 4 is an even number. So events might or might not occur together. So, if you take two events, it might or might not be possible for them to occur together. If there are two events for which it is not possible for them to occur together, then that's a special class of events and they are called mutually exclusive events, and for those events the set of outcomes which favor A and the set of outcomes which favor B they do not overlap. So, as sets they are disjoint. Okay? So, that's the concept of mutually exclusive events, and the importance of mutually exclusive events is that if you take two mutually exclusive events A and B and take their union, so this is the event that A occurs or B occurs, then the probability of A or B is the sum of the probabilities of A and the probability of B. Okay? And you can think of it in terms of the size of the set A union B divided by the size of S, but the size of A union B, if A and B do not overlap, if they are disjoint subsets, is size of A plus size of B, so that exactly splits as a sum of A over S plus B over S, and that's exactly the probability of A and probability of B. Okay? Here, any questions? The next concept is the concept of principle of inclusion and exclusion. So, if A and B are events, then probability A union B, which is where A union B is the event that A occurs or B occurs, is equal to the probability of A plus probability of B minus probability of A intersection B. So, A intersection B is the event that both A and B occur. Okay? And this is any problem? Okay. This is an example of a situation where you have the inclusion and exclusion principle, which you can also think in terms of sets. So, if you have two sets A and B, then their union or A or B, that event in terms of probability, is the total shaded region. So, A union B is a total shaded region. And you can write this as the size of A, shaded region with one kind of stripes, plus the size of B, shaded region with the other kind of stripes. But in doing so, you have counted the shaded region where A and B overlap twice, once for A and again for B. So, you should subtract the area of the shaded region where the two overlap, and this is exactly the intersection or the overlap of the sets A and B. So, this is the total shaded area, and you can write it as this kind of formula. So, if it is probability, you can now divide everything throughout by the size of the total sample space or the size of the total universal set, and exactly this is the probability that A union B or A or B occurs. This is the probability that A occurs. This is the probability that B occurs. This is the probability that A intersection B occurs. And this is exactly what you have as the inclusion exclusion principle. And any questions? So, an inclusion exclusion principle doesn't necessarily mean that you have to have only two events. You can do it with more events. So for example, here it is with 3 events. So A union B union C, which is the event that either it is the event that A occurs or B occurs or C occurs. So this is probability A plus probability B plus probability C. So first you do the naive thing and add everything up, and then you adjust for the overcountings. So then you adjust, so of course you have counted A intersection B twice. So you subtract once. You counted B intersection twice, subtract 2. C intersection A twice, subtract. But now, since there are 3 events, there is another set which you have subtracted a bit too many times, which you have subtracted 3 times, which is a set where all these 3 intersect. So you adjust that back by adding A intersection B intersection C. Okay? And so on. So if there are 4 sets, what will happen is that first you will take the probabilities of the single set with plus sign, then you will take the probabilities of the intersection of 2 sets, all possible intersections with minus sign, then you will do the intersection of 3 sets with plus sign, and then you will get the intersection of 4 sets with minus sign, and so on. So what I am saying is that it's, as I already pointed out, it is inclusion exclusion principle does not only apply to 2 sets, you can extend it to the sets, and just as a preview, you can sort of extend it to any number of sets where the probabilities of the intersections of a certain number of sets will occur with alternating signs. Okay? Any questions? Okay. So let us continue with another example. So a glass jar contains 1 red, 3 green, 2 blue, and 4 yellow marbles. So if a single marble is chosen at random from the jar, so what is the probability that the chosen marble is yellow or green? Okay, so you are asked to calculate the probability that the chosen marble is yellow or green. So Y union G, if you think of them in terms of set. And notice that these 2 events are mutually exclusive. So a marble can be at all green or yellow. It can only be yellow or it could only be green. It cannot be both at the same time, right? So these are mutually exclusive events. As sets, they are disjoint. So the probability of their union or the probability of their OR is the sum of their probabilities, and then you easily calculate the sum of calculate these individual probabilities by saying that the probability of Y is the total number of yellow balls by the total number of balls, which is 4/10. Similarly, the probability of green is the total number of green balls divided by the total number of balls, which is 3/10. So total probability of getting a yellow or a green ball in a single draw is total 7/10. Okay? Any questions? So let's now look at an application of the principle of inclusion and exclusion and calculate the probability of the union or the OR of 2 events which are not mutually exclusive, so which can occur together. Okay? So there you have to use the full principle of inclusion and exclusion to get the answer. So if you want the probability of king, you choose a single card chosen at random from a standard deck of 52 cards. So what is the probability of choosing a king or a club? So of course you can choose a king, you can choose a club. So how many ways of choosing a king are there? There are 4 ways of choosing a king because there are 4 suits, each suit contains 1 king. How many ways of choosing a club are there? Well, a club is a suit. So there are 13 cards which are clubs. So you could choose any of those 13 cards and get a club. Is there a way of choosing a king and a club at the same time? The answer is yes. Because you could go to the suit club and you could choose the king of that suit. So you could choose the king of clubs and you will get a card which is both a king and a club at the same time. And in fact, there is only one way to choose a card that is both a king and a club at the same time, and that is to choose the king of clubs. Okay. So what is the probability of getting a king or a club? So by the principle of inclusion and exclusion applied to two events, king and club, you get this as the probability of king plus the probability of getting a club minus the probability of getting a king intersection of club. So both a card which is both a king and a club at the same time. So what is the probability of getting a king? Well, there are 4 kings, so 4 out of 52. Chance of getting a club, 13 clubs, so any of those 13 will do out of total 52, minus the probability of getting a king and a club at the same time, which is to pick the king of clubs out of the total 52 choices, and you can simplify this as 4 over 13. Okay? Any questions? Okay. So let us now go on to the next example, which is to do with integers. So an integer between 1 and 100, both 1 and 100 inclusive. So anything starting from 1, 2, 3, 4, up to 100. So an integer between these numbers between 1 and 100 is chosen at random. Find the probability that it is a multiple of 2 or 3 or 5. So what is the total sample space? So let's start with that. So total sample space is 1, 2, 3, 4, up to 98, 99, 100. So how many? What is the total size of the sample space? Is 100. Easy. So so let A, B, and C be the event that the chosen integer is a multiple of 2, 3, and 5 respectively. So what you are asked to find is that the chosen number is a multiple of 2 or a multiple of 3 or a multiple of 5. So in terms of events, it is A union B union C in terms of sets. And you want to calculate the probability of that. So for notational convenience, we will denote xk to be the set of integers which is a multiple of k. So in particular, we will be interested in x2, x3, x5, right? So what is, how many, so x2 is the set of all integers, all numbers between 1 and 100, which are multiples of 2. So that is the even numbers. So how many there are between 1 and 100? There are 50. How many multiples of 3 are there between 1 and 100? Well, you just divide 100 by 3, and of course there will be a remainder of 1, that's the excess, but it's like 3, 6, 9, 12, up to 99. So how many are there? There are 33 total. How many integers are there which are between 1 and 100, which are multiple of 5? Well, 5, 10, 15, 20, etc. So how many times you can fit 5 inside 100? That's 20, right? Because 100 is 20 to 5. So that's 20 integers which are multiples of 5. So now, the idea is that we are going to use the principle of inclusion exclusion. So this is going to be probability of, we are asked to find the probability that our number is a multiple of 2 or a multiple of 3 or a multiple of 5. So this is the probability of A union B union C, and this is by principle of inclusion exclusion. This is probability of A plus probability of B plus probability of C minus, with minus sign, the probability of the pairwise events plus the probability of the triple intersection, right? So now we have to, so using these informations, we will be able to calculate the probability of the single events. So now we have to calculate the probability of the pairwise intersections. So what is the event that the number is, what is the event A intersection B? It means that the number is divisible by 2 and the number is divisible by 3. So it's a multiple of 2 as well as a multiple of 3, which is exactly the intersection of the sets x2 and x3. And if a multiple number is divisible by 2 as well as 3, then it must be divisible by 6, right? So, in other words, we are looking for all the numbers which are divisible between 1 and 100, which are divisible by 6. So, how many are there? Well, 6, 12, 18, 24, up to 96. So, there are 16. Similarly, x2 intersection x5 is related to the event B intersection C, and that's exactly equal to the set of numbers between 1 and 100 that are divisible by 10. So, it's 10, 20, 30, 40, etc. up to 100. So, there are 10 of them. x3 intersection x5 is exactly the set of numbers which are divisible by 15 and are between 1 and 100. So, 15, 30, 45, up to 90. So, it's 6 of them. And finally, we need to calculate eventually A intersection B intersection C. So, that is the set of all numbers between 1 and 100 which are multiples of 2, which are divisible by 2, divisible by 3 and divisible by 5 at the same time. So, that is divisible by 2 into 3 into 5, which is 30. So, how many numbers which are multiples of 30 are there between 1 and 100? Well, 30, 60, 90, that is it. So, there are 3. So, now let us calculate the probabilities and plug everything in. So, probability of A is 50 over 100, probability of B is 33 over 100, so 0.33. Probability of C is 20 over 100, so 0.2. So, this pertains to B intersection C, A intersection B, this pertains to B intersection C, this pertains to C intersection A, and this pertains to A intersection B intersection C. Okay? And then you just calculate these probabilities and plug everything in to the principle of inclusion and exclusion and get the answer as 0.74. Okay? Any questions? So, let us now go back to one of our motivating problems, which was the birthday problem, and revisit it. So, now let us, with all this discussion about probability theory that we have done in this lecture, let us try to understand, let us try to see if we can sort of get a more concrete understanding of the birthday problem and why the answer might be larger than you might feel at the beginning. So, in a group of n people, what is the probability? So, let us solve it for general n. So, suppose there is a group of n people, what is the probability that there are 2 persons having the same birthday? Okay? So, the way we will calculate it is to calculate the probability of the opposite event and then subtract it from 1. So, this pertains to this pertains to the concept of the complement of an event, which is saying that the event A does not occur. Okay? And if the total probability is 1, so the probability of that the event A does not occur is 1 minus the probability of A. And how do you see that? Well, the event A does not occur means the outcome is in all the outcomes in S which are not in A. So, it is in the complement of A. Okay? So, this is complement of A as a set. So, all the possible outcomes of the random experiment, all the possible outcomes of the experiment, all elements of S which are not in A. So, all the outcomes of the experiment which are not in the event A. Okay? So, what is the size of this event when you of the event A complement when you think of it as a set? It is the total size of all possible outcomes, total number of outcomes minus the outcomes that favor A, right? So the total number of outcomes which do not favor A is the total number of outcomes minus the number of outcomes which favor A. Okay? So let's now consider this. So this is what we have, and let's now divide everything by this total number of outcomes. So this is exactly the probability of A complement or the probability of A not occurring. This is 1, and this is nothing but minus the probability of A occurring. So the probability of A not occurring is 1 minus the probability of A occurring. Okay? So that's the idea. And A not occurring, the event that A does not occur is the complementary or the complement of the event that A occurs. Okay? So let's now go back to the birthday problem. So suppose we are having n people in the room, and what is the probability that there are 2 people having the same birthday? And the way we will do it, so actually what happens, and this also happens in many other calculations of chance of various events, is that I might be interested in calculating the chance or calculating the probability of a certain event, but actually it might be much easier to compute the probability of the opposite event. So it might be actually much easier, as we shall see in this example, it might be actually much easier to compute the probability of that event not occurring. So what we will do is that we will do the easy thing and compute the probability of that event, of our event not occurring, and then subtract the probability of not occurring from 1 to get the actual probability of our event of interest occurring. Okay, so that's how we will proceed. So the probability that there are 2 people having the same birthday in a group of n people is 1 minus the opposite event, which is 1 minus the probability that all the different people have different birthdays. Okay? And it is this probability that we will calculate. So let's go about calculating this probability. So there are a group of n people, we want to calculate the probability that all of them have different birthdays. So what is the total number of possible outcomes? So every person, each one of these n people can have birthdays on any one of the 365 days in the year. So the first person can have any of 365 possible birthdays. For each possible choice of birthday for the first person, the second person can have any possible day of the year as his birthday. So 365 more choices, so times 365. And so you go on multiplying 365 n times for n people. So the total number of possibilities for the outcome of the random experiment is 365 to the power of n. So the probability that we want to calculate is when all the birthdays are different. So suppose, just by notation, let us denote by A to be the subset of the event where all the n persons have different birthdays. And let's count the number of ways of assigning birthdays to these n people so that all of them have different birthdays. So how many possible ways are there of doing that? So the first person can have any of the 365 days of the year as a birthday, so no restrictions. For each choice of birthday for the first person, now for the second person we have a restriction. Because we want the n persons to have different birthdays, so the second person cannot have the same birthday which I have picked for the first person. So the second person, for each choice of the birthday for the first person, the second person can have any other day of the year as the birthday. So 365 minus 1 day which I have chosen for the first person. So 365 times 365 minus 1. Now I have chosen birthdays for the first 2 persons. I go to the third person. What is the restriction? For each choice of birthdays for the first 2 persons, the third person can have any day of the year as his birthday except for the birthdays of the chosen for the first 2 persons. So there are 365 total number of days in the year, and the first 2 persons have 2 distinct birthdays, so 2 days are not available. So I can assign the birthday for the third person to be any of the 365 minus 365 days of the year minus the 2 days which contain the birthdays of the first 2 people. So times 365 minus 2. And you go on doing like this. So for the nth person, you can choose any of the 365 days of the year as his birthday, except for the n-1 days which have already been assigned as the birthdays of the previous n-1 people. So you multiply all these factors together, and you immediately see that you can express it in terms of factorials that we have learned in the counting lecture as 365 factorial divided by 365 minus n factorial. Okay? Because the last one is 365 minus n plus 1, so you multiply top and bottom by 365 minus n factorial, and this is exactly 365 factorial divided by 365 minus n factorial. Okay? So the probability that two people have the same birthday is the probability of the complement of the event that they have all different birthdays. So probability that they have two people have the same birthday is probability of a complement, that is 1 minus the probability of A. So 1 minus the size of A divided by the total number of possibilities, which is 365 to the power of n. So the size of A divided by 365 to the power of n. So this is of course a large number, but with the help of calculator or computer or some computing gadget, you can calculate this, and you will be, and of course this increases as n increases, and you will be surprised to know that even for n, even as low as 23, already the chance is more than half. So the chance is more than 50% that in a group of 23 people, at least 2 people have the same birthday. And today, and by the time you reach 50 people, in a group of 50 people, the chance that 2 people have the same birth, at least 2 people have the same birthday is more than 99%. So today, I believe we are somewhere between 30 and 40 people in this room, so it's already more than 70% chance that 2 of you have the same birthday. Okay? So now, I leave you to the task of finding out which 2 of you have the same birthday, or maybe there are many coincidences like this, and end our lecture here at this point today, and we will continue in the next class. Okay?